Hello, hello.
Hello, hello, test, test, test.
Hello,
Okay.
hello. Yep. Okay, everyone. It's 2:30. No, is it 2:30? Are people awake? I know, it was a test. It's 1:30, everyone. We had some food, we had some coffee, so how about we get started on part 2 of today? And to get an amazing start to this next session, we're going to have Danielle Berg telling us a little bit about relationship between star formation and chemical evolution.
All right, thank you very much. I am so excited to be here. I haven't been to Space Telescope since before the pandemic, so it's really wonderful to be back in this vibrant community with a big group of wonderful astronomers. I also want to just say right off the bat, of course, that trying to give a review of a broad topic in any amount of time is really challenging, so I'm definitely not going to cover all the works that's related to chemical evolution with star formation and everyone's work in this room. So I apologize in advance, but I look forward to hearing about all your other work throughout the rest of the conference. So I'm Danielle Berg. I'm an assistant professor at UT Austin. And I'm going to kind of broadly tell you about some of the things that I think about chemical evolution. And starting really basic. Okay. So chemical evolution, one of the reasons I love to study it is because it is directly shaped by the star formation. So start with our really simple picture. We know that we have, pristine gas, stars form, they create metals, they die, they put them back into that gas and slowly enrich. So we see that generations of star formation increase our metallicity, and so metallicity in turn then is really a tracer for that past star formation history, kind of thinking back of the family tree of what's happened in these galaxies, of giving us a good way to mark how much evolution has happened in these galaxies as a whole. Now, we all know, of course, that the picture isn't quite this simple. And have we really not seen this session yet? Usually it's like every talk, right? First one, okay. So, on top of just having stars create our metals, we know that it's this really complicated interaction where we have accreting gas that can come in, that can dilute, that can trigger star formation. We know that we have feedback that can redistribute metals within the disk as well as eject it out into the circumgalactic and intergalactic medium. We have these complicated processes that are also shaping what not just our total metals look like, but also our relative abundance patterns. Now, studying these things, I'm going to tell you a lot, about how we do this across cosmic time, and in particular, for this, the ultraviolet and the optical has been really powerful because we've been able to use things like the Hubble Space Telescope at redshift 0 to do detailed UV studies at redshift 0, and we can do optical from the ground, of course. And then, when we go to redshifts like 2 to 3, we can start to get the UV from ground-based telescopes. And I don't actually know what HAB World is going to look like yet, but this is one of the images that was on the internet, so we'll be able to do really detailed studies in the future at redshift 2 to 3. And then, of course, with James Webb, it's opened this window of very high redshift galaxies of being able to look at both the UV and optical of these things in the infrared. And so it's really powerful to be able to do the same regime across all of galaxy evolution. Now, what do we talk about when we measure metals? This is actually really complicated. So if we just take like a star-forming region in a galaxy, and we want to take some spectra of this, there's a couple different things we can do. First of all, we can look at down the barrel absorption line, so gas that's in front of the stars, and look at the different absorption lines that trace the different metals that are there, and get these neutral gas abundances, and ionized abundances along those lines of sight. Then we have the gas that's surrounding the stars that are ionized, so that we get these emission lines. We can get a whole bunch of different elements. And we do this both in direct method, meaning we're actually measuring the gas properties, and we also can do this with strong line calibrations. And then third, we can actually measure this directly from the stars, and in particular, if we do this from like supergiant stars, these are recently formed stars, so they should have the same chemical makeup as the gas that you're looking at right now. But in this case, we're matching like a total abundance pattern. We're not looking at the variations amongst different elements. And this is great that we can do all of this, but first of all, you're going to notice that we measure different metals in these different methods, and they all have their different caveats and challenges. And so I like to say, like, we aren't comparing apples to apples all the time, right? We're comparing apples and limes and lemons and peppers or something like that. Further, there's a lot of different things that we can try to trace within a given spectrum. So these, is an optical spectrum here. And we can get, really wonderful lines. I'm just highlighting a few of them, but lots of these recombination lines in hydrogen and helium. Those are really, really strong. But we can also get these really faint, like oxygen and carbon recombination lines that are typically about 1/1000th the strength of H beta. And we can get things like these collisionally excited lines, which can be really strong for things like oxygen 2 and oxygen 3. We've got some sulfur 2, we have some argon 3, some sulfur 3. But then when we look at things like the temperature sensitive lines like 4363, that's going to be about 1/100th of the strength of H beta. So it's still challenging. And we can also get some interesting information from things like the nebular continuum, where we see like the Balmer jump, which is also temperature sensitive, or the Paschen jump. In the UV, we get a rich source of features as well. There we go. So in the ultraviolet, we can trace a bunch of other things simultaneously as well. So first of all, we can actually trace like the very massive stars using their stellar wind and photospheric properties. This can tell us like the metallicity and the age of the very massive stars that are there to about 40 million years. And then we can also get these absorption lines that I was showing you earlier down the barrel. And we can also get some other collisionally excited nebular lines that are there too. Now to do this really, really well, what we actually want to do is be able to measure the properties. So you can look at these different diagrams, and what's really nice is if we want to do direct abundances in the optical, we can either use recombination lines. I told you these are really, really faint, so they're hard to do, and we can only do them in very nearby galaxies. If we use our collisionally excited lines, the challenge here then is that we have this exponential dependence on temperature. But if we take like the same ion, so that we get rid of other sensitivities, all we have then is that one of the lines comes from a different level, and so it's going to have a different temperature sensitivity than the other one. So we take those ratio of those two lines, measure the temperature directly, we can put it back in, and then measure, this just depends on how many ions are there then once we have the temperature and density, and we just add up all the ions to get a total abundance. Works pretty good. But to do this then for like all ions, all metals, this means that we actually have to measure all the temperatures, densities, ionization parameters, things like that across the entire nebula. Typical H2 region defined by where hydrogen's ionized, typically out to where oxygen 3 ends. But we are finding in a lot of things, especially at high redshift, but this has been known for a long time in like compact blue dwarf galaxies, we'll see helium-2 emission is coming from this very high ionization zone. And we actually need to then have temperatures, in each one of these zones to do this really, really well. Now, that's not always possible, so instead we use things like temperature-temperature relationships to relate them. And here looking at high ionization O3 versus intermediate ionization sulfur 3, and then intermediate ionization sulfur 3 versus low ionization nitrogen 2, what you'll notice is that if we color code by oxygen 3 to oxygen 2, which is basically an ionization parameter diagnostic, these do better or worse depending on what you're looking at. So nitrogen 2 and sulfur 3, which trace lower ionization gas, do really well in lower ionization gas. Okay, that makes sense. So do we actually have the right temperature diagnostics for the dominant ionization zones in the galaxies we're looking at? That's a really important part that we don't always have access to the exact diagnostics we want to use. And this becomes really important in the different lines we want to measure because these lines are not only dependent on their ionization, but their excitation potentials. So, we have a Maxwell-Boltzmann distribution for whatever temperature our gas is. And for something like oxygen 3, if we're at, fairly low metallicity and a temperature of 15,000 Kelvin, this is pretty easy. We populate this distribution pretty easily. But as we start to go to, some of our other lines, like this is why 4363 is so much fainter, because it's much, it requires much higher excitation energies in order to see that line. And when we start going to the ultraviolet, which becomes really important for high redshift, 1666 requires even higher excitation energies. So we need really high temperatures to populate these emission lines, to collisionally excite them. And something that a lot of people have been excited about is lately, nitrogen-3 at 1750 also requires a really high excitation temperature. So we need to know these temperatures well, and we need them to be pretty high in order to actually get these emission lines. Oh, and there's nitrogen-4 for you, even higher. Okay, so another big challenge is, what are we actually taking a spectrum of when we do metallicities? So first of all, if we're looking at low mass dwarf galaxies, we know that they're like not perfectly distributed. Now, it's been known and studied for a long time that there could be temperature fluctuations within these. It's still an open question, though, about how significant the actual abundance fluctuations are that result from that. And it doesn't seem like they're probably super significant, but what you infer can be biased based on the temperature fluctuations. For spiral galaxies, disk galaxies, definitely not a uniform abundance. We have gradients in them. And so if you're doing big surveys and you're just like targeting the center of the galaxy, we're biasing, obviously, what we're looking at here. And with James Webb, with slits that are in certain places, sometimes we're only getting part of the galaxy. So what portion of it are we actually probing? What metals are we getting? So that's something else we need to worry about when we're trying to compare samples of galaxies. So when we don't have direct metallicities, then we can use our stronger emission lines. So we said 4363 is very weak. But instead, we can use these really strong emission lines to try to do strong line calibrations. A long-standing example is the R23, oxygen 2 and oxygen 3 over H beta. And then you can use that with a whole population of galaxies where you measure the metallicity directly, you relate it to this strong line diagnostic, and you get a trend that you can then use to measure the metallicity of lots of galaxies that you don't have all of the temperature-sensitive lines for. So this has been, hugely successful in giving us, these scaling relationships for galaxies that they build up in metals and mass, this evolutionary trend from the Sloan Digital Sky Survey for hundreds of thousands of galaxies, such as Tremonti 2004. So this is really powerful to characterize populations of galaxies. But when we want to start looking at evolution, again, what are we doing for apples to apples? So first, I just love the mass metallicity relationship in general because it allows us to kind of look at how our tiniest dwarf irregular galaxies start to relate to our disk galaxies and then to our giant ellipticals and putting them all together. And these strong line diagnostics have typically probed these more massive galaxies, and they're offset from lower mass galaxy direct metallicity measurements. Now, what shapes this is several things. We have our star formation in general. We've already said we make more stars, we get more mass. They put out metals, so we increase along this relationship. We can also get pristine inflows, which can first dilute our oxygen abundances, but it can also trigger new star formation that causes us to go back up along this relationship. We can also have an enriched outflows, that we create new stars, but we can then just totally carry that oxygen with us and kick it out of the galaxy sometimes. Oh, yeah, and those are my lemons and limes again to show the comparison. Okay, so a big win that you may or may not be aware of in the nearby universe is that we have been trying to actually look at different ways to measure these metals. And in particular, again, this is just our mass metallicity relationship, slightly different format. And we have a model that's shown here in green, and then we have a bunch of galaxies that are blue. So these are metals that have been measured from their blue supergiants, as well as some that have been measured from the red supergiants and superstar clusters. And then you have gas measurements from the Sloan Digital Sky Survey. And we find pretty good agreement overall from these different galaxies of different mass. So we can start putting together this mass metallicity relationship at redshift 0 from stars and gas that agree. That's really exciting. Now, when we ask what's the actual correct way to measure direct gas abundances, another thing to look at then is, let's say the stars are the truth. So we have a stellar abundance on the x-axis, and then we're going to look at the deviation from the stars minus the gas. And we have two different measurements here, our collisionally excited lines, so that's where we have to measure the temperature, and then we have those really faint recombination lines in boxes. And something that's really interesting is that what you see is that below solar, at lower metallicities, we're finding that there is scatter, but the collisionally excited lines are actually doing a really good job of matching the stars. This is another big win for how we measure metals. But once you get to higher metallicities, then the recombination lines do much better. It's also, becomes incredibly difficult to actually measure temperatures at those metallicities. So part of it is it's easier to measure recombination lines here as well. But this is, I think, better than we thought it has been for a long time. So this is exciting. Now, if we go back to our mass metallicity relationship in general from gas phase abundances, we also then start to ask ourselves, well, does it evolve? If we look at just strong line abundances, we can look at some different studies that have happened over the years, looking at what used to be high redshift at redshift of 3. And from strong line abundances, not always the same ones, we'd see this extreme evolution. And then there was a lot of work that was done with like Alice Shapley and Ryan Sanders to work and try to actually stack things and get direct metallicities at redshifts 2 to 3. And you can see they're much closer to this redshift 0 relationship than using the strong line evolution. Now, why we want to do this, why we want to really understand this evolution is because it's really important to understand our cosmological simulations, to tie this back to star formation, to constrain the feedback and the different prescriptions within them. So this is just showing you some of these different cosmological simulations at about a redshift of 2. And so you can see some of these are SAMs and some of them are just regular simulations. And what's really interesting is that if we actually look at these at different redshifts, we see pretty significant differences in their slopes. Now we have the mass metallicity relationship slope as a function of redshift, and they're pretty different. They're pretty extreme. So if we had a consistent, robust way to actually measure this across redshifts, this would be an incredibly powerful constraint on what the correct prescriptions are for our simulations to get feedback right. Now, we want to do this across all of cosmic time, so to actually do this at very, very high redshifts has been very challenging, and JWST has opened the window onto this. There are really exciting programs. I know we'll hear a little bit more from Ryan later about how this is being done at redshifts 2 to 3 with actually statistically significant samples with direct metallicities. That's really exciting. But at the highest redshifts, above redshift like 6, here's a nice paper that actually goes down to, well, you can't see at the top, but like redshift 4 from Rashida 2024, but we only have like 10-ish galaxies so far that we've measured at a redshift of above 6 with a significant direct metallicity measurement. So this is still like the frontier. It's still wide open. We still don't really have good answers for this. But we're seeing really incredible spectra, extremely strong emission lines, things we don't really see in the nearby universe. People asked about that yesterday. Well, like, how don't they match? The first way I will tell you is the equivalent width of these lines. We absolutely do not see the equivalent width of these emission lines in any nearby galaxies. And I try to find the most extreme ones, and I'm like, they're close. They're as close as we can get, but they're still nowhere near the strengths. Like, we do not see these things. This is just crazy. We don't see this at redshift 0. Even these equivalent widths in AGN, they're really, really extreme. So this is telling us something is different at high redshift. Now, we want to, like I said, be able to actually do these evolutions of the mass metallicity relationship. We only have so many galaxies to look at so far, but here are some of these high redshift galaxies, and trying to constrain this above like redshifts of 6, looking at stellar mass versus oxygen abundance. Some of these are upper limits, some of these are direct measurements. And then actually comparing these best fit relationships. So you can see the best fit relationship from this Morishita paper here in this goldish line, and that line I was showing you before. Well, I guess, yeah, this line is not the same one I was showing you, but it's really close. This is from a survey that Bethan will tell you about. And you can see that they are offset from one another. So this is still not a ton of data points, and so we really want to understand this better. And other people have looked at this at some different higher redshift regimes, and we're getting a variety of different answers. So we definitely need more time to work on this. The other thing that's really, really interesting is if you take these different data points that have been measured at high redshift, redshift 5 on this one and redshift 8, we can also compare these to some updated simulations. So these are the FIRE 2 simulations. And from at least redshift 5 to redshift 8, very high redshift, you can see that the data points aren't showing significant differences in the observational measurements. And the Fire 2 simulation similarly does not show significant differences. So at least in the early universe, it doesn't seem like the mass-metallicity relationship was evolving very quickly. But I think somewhere between like redshift 5 and cosmic noon, we're seeing some pretty significant evolution. That's what it's hinting at. But that's still to be filled in. All right, and so going back now to this stars versus gas comparison, where we are having a really big challenge is then comparing to the stars at higher redshifts. So to give you an example, here's a nice plot added on here from Kashino 2022, and it also includes the comparison work from Cullen 2019. And you see that the stars here are quite offset from our redshift 0 trend. They're quite a bit lower. And in particular, if we look at this other plot from Kashino, showing here Ryan Sanders' work, 2020, of the gas at redshift, about 2, and the stars at redshift 2, even those are significantly offset. And so this is an open question. There's, of course, been this alpha enhancement suggestion where we just haven't gotten enough iron back from our type 1a supernova yet. That's all, certainly probably contributing to this. But we also have, a big uncertainty of what the actual star formation histories are of these galaxies. And you get very different results if you assume a constant star formation history, which a lot of people do, versus different bursty, non-parametric star formation histories. And so this is something we still need to sort out. Going a little bit further, well, we can't do direct abundances on that many very high redshift galaxies yet. So we think that the conditions are significantly different in these high redshift galaxies. So we need to recalibrate our strong line abundances. So this is one example of a couple of papers that have come out in the last year or so. This one from Ryan Sanders, 2024, looking at these different relationships of both moderate redshift galaxies and then these high redshift galaxies, 2 to 9 here from JWST. And there's quite a bit of scatter, but I'm still kind of throwing my weight behind these diagnostics that use oxygen, so R23 and O32. Just use oxygen 2 and oxygen 3, and I think that's really powerful. First of all, with this trend here, can I share my pet peeve with you? Okay. People have been calling this, it's been flipped, and they've been calling it the oh no plot. And I'm like, N is nitrogen, right? Can we all agree on that? We've had an oh no plot for a long time, right? It's N to O and O to H. So this is the oh neo plot, okay? That's what we all gotta start saying, oh neo. And it's like, oh neo. I don't know, something like that. But we also aren't completely convinced that neon to oxygen is that stable abundance that we think it is. There's abundance variations that we measure in the local universe. It's not a constant ratio. We don't have that fully figured out yet. And so this becomes really dependent on a lot of different factors where if you're using just oxygen lines, you take out one of those uncertainties. So I really like that. And an attempt to do that is this updated work here where they've taken a different version, more of a polynomial that just uses the oxygen 2 and oxygen 3 to try to fit these high redshift galaxies. So this is ongoing work, and as we get more direct abundances, we'll be able to calibrate it better. All right, I also wanted to mention, like I said, this neon work that Carla Ariana Cordova worked on. This is showing you nearby galaxies of a whole bunch of different sorts, star-forming galaxies, H2 regions, galactic H2 regions, enhanced star formation nearby galaxies. And there is a huge scatter in neon to oxygen. A lot of times we like to think these alpha element ratios are constant, and it doesn't just stay there. So that's a really hard assumption. Carla also looked at whether or not neon to hydrogen evolved, and there might be some hints that this actually is evolving as a function of redshift, and so that's also something we need to pay attention to is, are we even assuming the right neon for the redshift we're looking at? And then third, you really need to measure the temperature. It's so important because when you actually measure the temperature in all of these things, you get relationships that look like this. If you use the exact same data, but just assume a temperature of 15,000 Kelvin, you get this. It looks very different. You actually have to measure the temperature. It makes a huge difference. And people are attempting to do this. There's a ton of people that have tried to do this. I didn't get to put everybody on this slide. Matilda, wherever Matilda is, Matilda's done a ton of work on calibrating these things, trying to calibrate the UV based on the optical, and we still have huge dispersion. This is something we do not have well calibrated. We need to work on better. All right, I got hardly anywhere in this talk of where I wanted to go. Nitrogen is super complicated. We get primary production. That means it doesn't depend on the initial metallicity. This is just kind of your standard hydrogen, helium put in. How much do you get out? But we also get this secondary component from the CNO cycle. We have this nitrogen-14 bottleneck. We get dredge up. It can blow out of the stars, but it depends on your initial carbon and oxygen seeds, and so it doesn't turn on until you have enough to do it. But nitrogen is even more complicated than that, because it's also time dependent and can be affected by inflows, where we would shift this way. It can be affected by outflows, which would shift you this way. And we just get this huge scatter in general, because nitrogen is predominantly produced by AGB stars, 100 to 400 million years after star formation. Oxygen type 2 supernovae, about 10 million years. So they come on very different time scales, and so you get this scatter based on where you are in the clock of your star formation. Oh, yeah, so I decided to show that to you. So oxygen enrichment puts you down here. Nitrogen enrichment from AGB stars takes you up there. And so again, where you are in your clock will give you a huge scatter. So you can sometimes get very low N/O if you've had you're super new in your star formation, you've had some supernovae go off, you can kind of scatter down here. And you can also then get very high N/O if you have older stellar population that's now giving you that nitrogen enrichment from your AGB stars. But what explains the crazy nitrogen we're seeing at high redshift? There's my time. I'll take one more minute of my questions. Okay. So this is GNZ11. This is redshift 10.6, nitrogen 4 and nitrogen 3. The only thing in the nearby universe that looks anything like it is Markarian 996. It doesn't have the nitrogen 4 really, has booming nitrogen 3. And this nitrogen 4 is very intense. It's related to density, and it puts it in the very high density regime, which tells us this is probably an AGN. But we can also just look at our theoretical models, and we need very high temperatures to produce this from the excitation, and it's very sensitive to the density that we're seeing. And there's a whole range of questions of what's actually producing this that we need to explore, which I think are super exciting. And I just wanted to point out that it's giving us really uncertain things. So this is Leo P, which we heard about yesterday from Grace Telford. It's a single O star, 3% solar. It has nitrogen 3 emission. I don't get it. If I measure N/O from the optical, I get low N/O like you would. If I measure it from both of them, I get high N/O. What does that mean? I don't know yet. I would love for you to talk to me if you have ideas. But in the high redshift universe, it could be that we're seeing very massive stars. It could be that we're having very massive Wolf-Rayet stars, or we're having really high density clusters that are all coming together. But look at what happens to the oxygen ejected at very massive stars. It drops kind of in this magical area while nitrogen stays kind of high. So it could be in these extreme conditions at very high redshift, we have the perfect conditions that we get this ejecta for a short time period from these very massive stars, and we're seeing them at this unique point. Okay. I'd love to tell you lots more about abundance stuff, so if you want to talk to me about it, please, come talk to me later. I'll just leave up my conclusions. And I was asked to say something about HWO. HWO is going to be so powerful for doing physics from redshift 0 to redshift 2.3, but we really need high spatial resolution, spectral resolution, and a decent field of view so we can actually start looking at how these things all work together. Thank you.
Thank you, Danielle, very much. It's an incredible talk. I'm a big fan of metal, so we're going to have a long conversation. Any questions for Danielle? One or two quick questions?
Thanks, Danielle. So you, of course, had your oranges and apples and lemons and limes or whatever for the metallistes. But I guess one thing that I'm wondering is how convinced are we that the stellar masses we compare between the dwarf galaxies and even the SDSS galaxies, but also the dwarf galaxies, the cosmic noon galaxies, and the redshift Ting galaxies are actually compatible to put those on the same mass metallicity scale, independent of the metallicity systematics?
I just said this to Bethan at lunch. I said they only told me to talk about chemical enrichment, so I'm not going into all the crazy caveats about mass, because I was like, this is just one axis, but the mass axis is a whole nother thing. So I agree with you. We need to work on that as well.
So I was impressed by the agreement between metallicity measured in the gas in the stars. And it used to be that there was a large discrepancy between the two. So what happened in the meantime? I must have lost something in some episode in this.
I think that you have to be doing the blue supergiants and the red supergiants, which requires very long exposures of high resolution spectra. You have to fit enough lines simultaneously to really constrain it. And so I think people like Ralph Kudrycki and Fabio Breslin have been building up these samples over the last couple decades, and they finally have enough to show that it statistically works. But I think that they've done a pretty good job for a long time, but other types of stars are really complicated. Yeah.
Okay, let's thank Danielle one last time, and we're moving on to the next talk. Okay, up next we have Beth and James, who's going to tell us about mapping multi-phase metals throughout star-forming galaxies. Thank you, Bethan.
Okay, thank you. So my name is Bethan James. I'm an ESA Aura astronomer here at Space Telescope. I'm going to talk to you today about some work that we've been doing recently, which would not have been possible without the people in this list here, and I've underlined the people who are in the room. Please go and find them. They've done a massive amount of work for what it is that I'm going to show you today. So, metals. These are the questions that light me up each day, and this is why I do the job that I do. I care about where metals are within the ionized gas, how they are distributed spatially within the ionized gas, and I also care about where they are between the two different phases. This is my traditional simplistic onion skin, now being called a stratified galaxy, with the hot young ionizing stars, the H2 regions where we get the hot gas, the ionized gas. And then this is this neutral phase further out, which is colder, where you get the bulk of the baryonic mass. And we can measure metals in the two phases, as Danielle was explaining earlier. And what I care about is what controls the amount of metals in each phase, and how that feeds into this big global picture of galaxy formation and evolution that all of you in this room care about. So for the optical, of course, we have these optical emission lines that we measure, and then the neutral gas, we get these UV spectra, typically from COS. So first of all, let's look at the ionized gas. Hopefully I'm not preaching to the choir here, but galaxies are not chemically homogeneous. We've now realized this after many years of IFU spectroscopy in the optical, and this I'm just showing you some hand-picked results here to demonstrate what it is that I'm talking about. So these are metallicity maps in typical star-forming galaxies in the local universe. First of all, we have HARO 11. This is beautiful MUSE data from Monaco, which shows a very big decrease here in the metallicity across the galaxy. And that's exactly where you have this accretion of pristine gas. So this is this beautiful link here between the metals and the star-forming regions, where the pristine gas comes in, it dilutes the metals, and then it triggers the star formation. Here we have NGC 4670, some work by Nimisha Kumari, also in the room. And this is an N over to O map, which you can directly rate to where the Wolf-Rayet stars are. And so here, using these maps, we can understand about self-pollution of nitrogen from these young clusters and these rapid mixing timescales that you get. And another different galaxy here, where we haven't got a good plot of it, but basically we can see that the metallicity structure echoes the stellar age structure. So this shows more kind of a stellar age gradient with long mixing timescales or stream-fed star formation. So this is kind of just an examples of what we know about galaxies and what we can learn from these metallicity maps in the ionized gas. It's not just the data that show us this. We can also see this in some of the more realistic galaxy simulations that we have. So this is some work by Andrew Emmerich, who's modeled, I think this is actually a model of Leo P, that extremely metapole galaxy that we've seen a couple of times already this last 2 days. And the orange is the ionized gas, and you can see that the metallicity as a function of time is jumping all over the place. And this is the scatter in the metallicity, and you can see that it's very big at each of these time steps. What piqued my interest, though, is that the neutral material, this cold, the blue line, is much calmer as a function of age. And what I'm interested in is why is that, what controls this difference in this erratic behavior between the ionized gas and the neutral gas? It is very dependent on the supernova rate for the ionized gas, and from these simulations, they find that there's much longer mixing time scales. So we're starting to look into this. Oh, apologies, Valentina, you've been blocked out for there. If you want to see her eyes, she's in the room. So this is a spatially resolved study of NGC 5253, where we have COS observations, different star clusters through the galaxy, and then we have MUSE observations of the entire one. So this gives us a perfect way to do a nice apples-to-apples comparison of the optical and the UV along the same line of sight. So we can measure oxygen, nitrogen, iron, sulfur in the neutral gas and the ionized gas along the same line of sight. And I'm not going to give you all the results, but this is a fantastic result that Valentina is going to be presenting in her poster on tomorrow. But what we've been able to find through this spatially resolved analysis of the two phases in this galaxy is where we see the oxygen here is a function of age, and the stars show you the ionized gas and the neutral are in the squares. So this is the oxygen, kind of a bit all over the place. The nitrogen, however, has a big offset between the neutral phase and the ionized phase. And you can see where you look at the NO to O here, as you get older in age, they start to agree with each other. So this is one of the first results that we've had that show us that mixing timescales are indeed between 10 and 15 megayears between these two phases. Like I said, there's way more results, and you can go see Valentina to discuss that. On the other end of the metallicity scale, we're also looking into a spatially resolved analysis of M83, which is supersolar galaxy. This is some fantastic work by Svea, who studied the oxygen abundances in the stars, the neutral gas, and the ionized gas. And you can see here is a function of radius. In the center, there's some crazy outflow stuff going on. But as you go further out of the galaxy, the gradients actually become comparable. So similar to what Danielle was saying, is that there is a good agreement in these high metallicity galaxies between the two phases in oxygen. And Adarsh Ranjan, whose also eyes have gone, is going to be doing this for nitrogen, sulfur, silicon, and iron in an upcoming study. But that's just one galaxy. We, of course, need a more statistically significant sample, as I keep on getting told in my Hubble TAC reports. So, so this is a COS Legacy Archive survey. This is a fantastic survey, PI'd by Danielle, myself, and some other people who aren't here today. But we have, this is COS data for 45 star-forming galaxies, nearby galaxies, that were selected according to their star formation rate, specific star formation rate, and ionization parameter to mimic galaxies in the high redshift universe. And we have COS data covering the far UV to the near UV, and then we have optically matched data from SDSS. So one of the, sorry, I'll explain. This is just going to play on loop, but it just shows you how beautiful the data are and how the different shapes of the continuum you get as it fills in the mass metallicity relationship here. So one of the projects we're going to do from Classy is compare the neutral ionized gas in 45 galaxies. This is what the galaxies look like, and many of them are quite compact to fit inside the COS aperture. So we have the ionized gas, and they're all T-based methods, incredibly accurately calculated by Danielle and Carla, and we're taking from these studies the oxygen, nitrogen, sulfur, and iron abundances, because those are the only elements we get to compare with the apples in the neutral phase. And this is going to be a theme, isn't it? The fruit and the peppers. Okay, this is the neutral gas. Kaylee Parker and Valentina have done an incredible job at fitting the absorption lines in 45 galaxies. If anybody's had to do this in the past, you know how epic that is. And so these are some of the examples. We have the iron triplet here, and this is a sulfur-2 doublet. So we combine these UV absorption line column densities with ionization correction factors from tailored cloudy models, and we take the column densities from Wade-Who's paper, another Classy paper in 2024. And with that, we get to make our comparison. So these are very preliminary results. I literally made the plots yesterday, so bear with me. As an over-preparer, this is not my usual way of doing things. But, so here we have the ionized gas on the x-axis and the neutral gas on the y-axis. And you can see up here, and this is just a 1-to-1 ratio in the dotted line here, and you can see there's a very nice behavior between the alpha elements, oxygen and sulfur. And we expect them to mimic each other. That's great. The iron is a bit all over the place, but that's also expected because there's a lot of depletion effects that happen with iron, where it depletes onto dust grains, and there's also, can be quite complicated with the ICFs for the ionized gas for the iron. So we're still working on this. Nitrogen, on the other hand, is not very well behaved, and it lands mostly in the ionized gas. So it has not been able to mix well between these two phases in these galaxies. So we're starting to try, remember what I'm trying to understand is what controls this mixing? What is the dominant factor that allows the two phases to mix and controls the mixing timescales of these galaxies? So I'm just starting to plot this offset here where I've just literally subtracted the neutral from the ionized. So if the galaxies land up here, there's more in the neutral gas. If they land below here, there's more in the ionized gas. And I'm going to plot things as just different properties. Okay, so what we can see here, this is very, very flat, that the mass of the galaxy, the stellar mass, really doesn't seem to have any effect on the amount of mixing between the two phases. Metallicity, somewhat maybe, if you kind of squint, maybe for the lower metallicity galaxies, there seems to be some less mixing, there's a bigger offset, and everything starts to agree more at the higher metallicity. Ionization parameter is interesting. The higher the ionization parameter, there seems to be more metals in the ionized gas, probably what we're expecting. Okay. And the stellar age, which is what I was expecting to show a really nice trend, not really. So as the stellar age gets higher, I was expecting to see the scatter to decrease, but we're not really seeing that result. But remember, compared to what we saw in NGC 52, 53, these are globally integrated values. So perhaps we're only seeing that nice age dependency when we look on just single cluster scales. What we are seeing, interestingly, is when I plot the outflow velocity as a function of this offset, we're seeing that as you get bigger outflows, there's definitely a decrease in the amount of metals in the neutral phase. They kind of more move into the ionized phase, which is very interesting. So, and kind of a similar result for star formation, but only for nitrogen. If you focus on the blue points, there's a trend. The rest is just, and who knows what's going on there. But the star formation rate seems to be the more star formation rate, the bigger the outflows, the less mixing. So we're not sure what's going on. So to carry on Danielle's questions here about nitrogen, why does nitrogen behave differently? Okay, what's causing this delay in the nitrogen mixing? There's been a lot of models actually talked about very early on. This is back in 2009 from Binet, who talked about these turbulent mixing layers in NGC 52, 53, where the high densities prevent this ejector from mixing well between the two phases. Is it because of the source of the nitrogen production? Is it because of the temperature of the gas? Is it so hot that when it's coming out, it isn't able to cool down quickly and see it in the neutral phase? Is it simply this timing effect, as this is taken from Danielle's paper? You can see there's, we're just managing to capture these galaxies when it's just been expelled into the ionized gas, and we're not able to see it cool yet. And is this what we're seeing at high redshift? Unless you've been under a rock for the last 2 years, GNZ11 is sparking a lot of interest, and we're starting to see some other examples now of these very high and over to O systems at high redshift. Again, is it any of these issues? Is that what we're seeing at high redshift with these very luminous galaxies? So I'm going to leave you with some conclusions, but they're mostly questions. So hopefully I've convinced you that galaxies aren't homogeneous with regards to the temperature content and metal content between the phases. We're seeing that alpha elements move well and mix well between the phases. The abundance offset seems to be mostly a function of outflow velocity when you look at integrated spectra. We can tie down mixing timescales now around 50 megayears, but nitrogen abundances are always seem to be higher in the ionized phase. And I'm going to leave you these questions to think about and ask, for more realistic simulations to try and understand and pin down what's going on in these metals. So, thank you.
Time for 1 or 2 quick questions. Run, Alex.
So when you're talking about the ionized phase and the neutral phase, so then you're talking about really the optical emission lines versus the UV absorption lines, right?
Yeah.
Okay, because some of those, the phases of those really actually overlap quite a lot.
Yeah.
So it's not like, it's more like warm and warmer, like 10 to the 4 and 10 to the 4 plus or something like that. But so what are you using for nitrogen in the UV?
There's a nitrogen triplet at 1134, 34.9.
Okay.
I use that triplet.
Nitrogen 2?
Nitrogen 1.
Nitrogen 1. Oh, okay. So that would be cooler.
Pretty cold.
Yeah. Okay, so that's cool.
Literally.
Okay, I think we're moving on, but definitely follow up with Bethan. And so we're gonna, sorry.
You're good.
So the next talk is going to be by Yuan Chen, who's going to tell us about robust chemical enrichment from strong emission lines.
Thanks. So I know it's about the time of the day when you start to fall asleep, but I'm going to tell you something very surprising, so keep awake. So my name is Yuan Chen. I'm a postdoc from UC Davis, and this is work done in collaboration with Tucker Jones at UC Davis, Ryan Sanders over there, and also grad students Erin Hunsinger and Paige Kelly. So I'm so thankful for Daniel to give us a crash course on this, so I don't have to go into details. But why do we care about this sort of things? Just quickly, because chemical evolution of galaxies reflects the star formation, gas fraction, and also flow of gas. So this is the famous mass mobility relationship that we can actually, with JWST, we can go to very far into the early universe. This figure, thanks Daniel for making it. This is one of my all-time favorite figure. So it really tells you like the carbon to oxygen ratio and with relationship to the gas phase metallicity, how different star formation processes and also gas flow processes can shape. And this is so nicely put together that you have all sorts of different kinds of objects, from DLAs to Milky Way stars to H2 regions, and they all fit very well into this figure. But there's a problem with the chemical abundance measurements in gas phase. And this is known as the abundance discrepancy. The reason is that there are two considered direct methods of measuring chemical abundance in gas, and one is from the optical collisionally excited lines, CELs, and this also commonly referred as the direct TE method. The other one is from the recombination lines. These are very faint emission lines, and it's very rarely been measured except from some local H2 regions. So if you compare the two methods, there's a considerable systematic offsets between the two. And this is referred to as the abundance discrepancy factor. So from these two direct methods, you can actually get about a factor of 2 difference in the metal enrichment that you measure. Usually the hypothesis of why this is happening is the temperature fluctuations. So the reason is that the optical strong lines, these direct TE method lines, these are very sensitive to your electron temperature. These curves, so for example, 577, 4959, 4363, these are very commonly used lines to do the direct TE method. These are, and over the typical range of H2 regions, their emissivity changes by several orders of magnitude. So the recombination lines, on the other hand, these dashed dotted lines are considered to be more accurate because they are not very temperature sensitive. So the reason this can offset your metallicity measurements because for very, so if you have a temperature distribution, for example, if it's Gaussian, your average temperature is here, but then because high temperature gas is very good at emitting photons, you're actually naturally biased toward high temperature gas. And this is why normally people consider recombination lines are more accurate. So we decided to test the theory with the far infrared fine structure emission. So right here, you can immediately tell these are temperature insensitive because their energy levels are so small. The other benefit is that they're also collisionally excited. So they share the similar emission mechanism as the direct TE method, but they are actually they should behave more like recombination lines. So we use the far infrared lines to test this temperature, directly test this temperature fluctuations hypothesis. And so far we have done this on 2 targets. One is called Markarian 71, and the other one is Haro 3. So we did this with several IFUs, actually. So one is the CAT KCWI, the other are far infrared of SOFIA 50LS and Herschel PACS. The reason we really want to use IFUs is sometimes people, oh, you're using KCWI to observe nearby H2 regions, it's an overkill. But no, because we need high sensitivity to observe the recombination lines, and also we need the IFU capability to do accurate aperture matching between these very different wavelength bands. And here is actually a good example of that. So Haro 3, the H2 region is actually on the side, and this is where the SDS aperture is pointing at. So if we just do classical way of doing aperture matching, it guarantees there's some mismatch between the two. So surprising result number 1. For Markarian 71, this is a kind of a busy plot I'll walk you through. The top one is the temperature measurements, and the bottom one is the metallicity, and x-axis is the density, electron density, because the far infrared are actually dependent on the density of the electrons. So remember, far infrared, joint far infrared, if there's temperature fluctuation, we expect them to be actually consistent with recombination lines. So, but in reality, we actually observe the joint IR metallicity to be consistent with optical CEL measurements. So this is your classical ADF, but we are actually, by directly measuring the temperature fluctuations using this method, we actually see that there's not enough temperature fluctuations to explain the ADF. Surprising result number 2, on Haro 3, we're actually not only be able to do with oxygen, but we also be able to do with nitrogen. So this is oxygen metallicity as a function of density. It's a similar plot as Markarian 71. This is your classical ADF. So at first glance, the oxygen metallicity seems to be actually consistent with temperature fluctuations, right? But when you go to the nitrogen to oxygen ratio, it's actually the other way around. So we expect the nitrogen to oxygen ratio, if we assume temperature fluctuations, perfect temperature fluctuations, the actual NTO ratio should be actually slightly lower than the optical strong line method, optical TE method. But in reality, the NTO ratio measured from far infrared is actually higher. And we actually consider, if you don't believe the oxygen to hydrogen ratio, we actually consider this to be more robust because we are comparing N2O both from far infrared here, and we are comparing N2O both from the optical. So there's no ambiguity in aperture matching anymore. So what happened? We believe that the temperature fluctuation is really unable to explain the N2O ratio here. So here I'm showing, this one is I forgot to label, I'm sorry, but this is the N2O ratio, the temperature fluctuation on y-axis, x-axis is the average temperature measured from the N2O ratio. These are from the oxygen. So you can actually see the N2O ratio really gives you a very unrealistic level of temperature fluctuations. It's actually starts to be comparable with the average temperature. But on the other hand, I think the smoking gun here is that in the N2H ratio, the far infrared actually gives you a similar level of offset in N2H compared to O2H. That means there's a similar amount of light being added to the O2, to both oxygen and nitrogen in the infrared lines. And our hypothesis is that there are very dust obscured pockets in your H2 regions. So optical, you really only pick up the low dust content, but in the far infrared, you start to see both. And that's where you added those more far infrared lights in there. So, but it also highlights the importance of testing temperature fluctuations in multiple ions, not just from oxygen. So future toward accurate abundance. So I hope I convince you, and also many people before me, convince you that the H2 regions are not spherical chickens in vacuum. These are, they are much more complex. So we need large sample. And unfortunately, we cannot no longer get more far infrared data, right? The SOFIA has been decommissioned. There's Herschel telescope is no longer usable as well. So we can only just do it the other way. So we are trying to get 30 more targets with direct oxygen and nitrogen abundances, trying to basically populate in optical, basically trying to populate this figure with more measurements. The other thing I just want to point to you about the opportunities with JWST. So in two aspects. One is that these are not only the far infrared emission. It's very nice to observe them in the far infrared, but also it's actually very beneficial to observe them in mid infrared as well, because there are some fine structure mid infrared emission with neon, for example. And this is done from archival Spitzer data and matching with KCWI. You can actually start to see, yes, because the Spitzer data we can, yes, I'm almost finished. So the Spitzer data, we can, in mid-infrared, there's the benefit we can actually observe the H. Humphrey emission, recombination line emission. So we no longer rely on optical data to get our H measurements. So, and the Spitzer seems to suggest that there's very low level of temperature fluctuation as well. The other thing is that with MIRI, MRS, they actually, we're actually able to spatially map the temperature fluctuations by comparing similar spatial resolutions from KCWI and MIRI. And the other aspect is that with very far, very high redshift galaxies, we can actually start to do this in JW, it's basically rest frame optical and rest frame far infrared. So it becomes JWST and ALMA. So we can, with redshift over 8, we can do this as well, start to do this as well. The other thing I want to mention is opportunities with HST. So we've already seen some sort of this figure many times. So gene Z11 has enhanced nitrogen to oxygen ratio. These are measured with, mostly conducted with the UV emission lines. So it's important to test this because the UV emission lines are more temperature sensitive than the optical emission lines as well. So it's important to test these with the UV emission line as well. So classy sample, Mathilde has this very nice paper measuring the UV temperature versus optical temperature. They seem to agree reasonably well. But we are trying to do a much better, basically a better constraints in the dust extinction correction or aperture matching, so we can actually measure, put a very good constraints on temperature fluctuation. And so far, the preliminary result seems to be that the UV emission lines has also suggest very low temperature fluctuations. So I'll leave it there. I hope I made your. I was hoping before beginning of this project, I was hoping we will make your life easier, but at the end, we're sorry because we discovered more complexities in these systems. And here are a summary.
We have time for one question. Danielle was, if Danielle's fast, maybe you can go in, Carla.
I was just wondering if you had the chance to look at the densities versus the different critical densities of these lines.
That's a really good question. So density fluctuations, if I go back here, there's a potential possibility that density fluctuations will offset your far infrared because these are density sensitive as well. That's why it's very important to do this in mid-infrared because the mid-infrared has basically the benefit of their much less temperature density sensitive and also less temperature sensitive. So we'll do that, but we constructed some toy models to try to explore that. So far, we don't think so, but also it's important to do the text even more.
Thank you. Very quick. So I want to understand what is the meaning at the t square lower than 0, because if we had 0, it means that we don't have temperature fluctuations. So what is the meaning of these very negative values? Are really realistic?
There's a reason why there's a preliminary on this figure, but also that's a puzzle. So we don't know. Dust could be. Aperture mismatching between the UV and optical could be another contributing factor. We're trying to understand why as well.
Thank you, Jung-Wan.
Yes.
And dust keeps coming back. So let's move on to the last talk before our coffee break by Metro Rewalski, who's going to tell us about mass, metallicity, and star formation rate for low-mass galaxies at cosmic noon.
All right, good afternoon, everyone. My name is Metro Rewalski. I'm a staff scientist for the Wide Field Camera 3 team on Hubble here at the Institute. And today I'm excited to tell you about our studies connecting mass, metallicity, and star formation rate for low-mass galaxies at cosmic noon. So up front, we're interested in two key questions. First, what are the metallicities of low-mass star-forming galaxies, which means we're going to be looking at the mass-metallicity relation. And so as was very nicely summarized earlier, this is a correlation between the host galaxy's stellar mass versus the gas phase metallicity, which we're typically tracing using the gas phase abundance of oxygen. And so as Danielle mentioned, the shape and offset of this relationship is shaped by a number of complex processes. At the high mass end, we have enrichment from star formation combined with balancing of pristine inflows. At lower masses, we have lower star formation rates as well as outflows due to having very shallow gravitational potentials in these galaxies, as well as a host of other physical effects. We're particularly interested in the low mass end because first, we have very numerous population of low mass galaxies that may significantly contribute to enrichment. And secondly, because eventually this relationship has to turn over. It can't continue going down forever, otherwise we just hit pure hydrogen and helium. And so before we can go ahead and tackle this, first we wanted to ask, do our existing strong line metallicity calibrations apply at higher redshifts? And notice I say higher, not high, because that has changed a lot recently. So we're interested in very low mass galaxies, which means they're faint, so we need very sensitive observations. And for this, we've been using the MUSE Ultra Deep Field. And so this is a unique region of the sky that contains two quasars at redshift 3.2 that are physically separated by only about 500 kiloparsecs, as shown in the green circles. We have a variety of multi-wavelength observations for this field, and I'll highlight the two most important ones. The first is 90 orbits of HST Wide Field Camera 3 near-infrared imaging and GRISM spectroscopy, which is the deepest HST GRISM survey ever completed for a single field. The footprint for that is shown by the red region, where we've gathered observations at 3 different position angles in order to account for overlapping and contamination of different sources. The second data set is 142 hours of MUSE optical IFU spectroscopy, reaching a depth of roughly 120 hours in the center and then becoming progressively shallower as we move away from the two quasars. And then we have a host of other observations such as rest frame UV photometry with HST, as well as serendipitous optical coverage with WIFPIC-2 from archival observations. And so the strength of these two data sets together is that they're both GRISM and IFU, which means there's no pre-selection of targets, there's no aperture effects. So we go as deep as we possibly can, and we see what turns up. So with these, we have 5-filter photometry and spectroscopy for over 1,000 sources, and we're able to get robust spectroscopic redshifts for over 400 sources that have split up into a lower and higher redshift sample shown in blue and orange respectively. And so really, I just want you to take away 2 points from this plot. The first is, for our higher redshift sample, looking at the stellar mass here, we're reaching stellar masses of less than 10 to the 8 for individual sources at redshift greater than 1. And in the next panel over for the star formation rate, for our lower redshift sample, we're reaching very low star formation rates, less than 10 to the 2 down to 10 to the minus 3 solar masses per year. So this opens up a really nice parameter space for us. So here's an example of what those observations look like. This is for a source at a redshift 2.3. We have MUSE in the upper left and WIFC3 in the upper right, with zoom in on the MUSE spectra in the center panels, and then our HST imaging at the bottom moving from red to blue, just to keep you on your toes. So what we can see here is in WIFC3, we get coverage of those nice, strong optical emission lines that we need for strong line metallicities. We have O3, H beta, oxygen 2, and then moving to MUSE, we have really nice coverage of the rest frame UV, in particular, this auroral or collisionally excited O3 1666 line that we can use in order to do direct method metallicities. So our second question first was, are existing strong line metallicity calibrations valid at higher redshifts? And so we know that the strong line calibrations are valid in the local universe. That's where they're calibrated for. They're based on huge numbers of SDSS galaxies. And as we've been hearing about, we're seeing a lot of strong evidence that they're not applicable at very high redshift. And so where does that start to break down? And so we already had a very nice summary of our two main methods, which first being the direct method. So we're using these temperature sensitive lines to get a very direct measurement of the metallicity with relatively few assumptions, where we're using O3 4363 below redshift 1 and O3 1666 at redshifts greater than 1. In addition, we have the strong line method, which is using those much stronger nebular lines, but of course, those strong line calibrations are tied to the assumptions of the direct method, and when we use that on other targets, we're making certain assumptions about the properties that they have in common. So in this case, we're using the strong line oxygen calibrations from Curdy et al. 2017, along with a Bayesian framework developed by Elena Henry in 2021 that allows you to marginalize over uncertainties such as extinction, stellar absorption, blending of lines, all of those types of things. So the first thing we did was go ahead and calculate metallicity using both techniques for targets where we had detections of these weak lines. And here are those results. So here we're looking at the metallicity determined from the strong line method on the horizontal axis versus the direct method on the vertical axis for the low and higher redshift targets in blue and orange respectively, with a 1-to-1 line in solid and factor of 2 agreement in dashed. And so kind of immediately what we see is that the results from both techniques agree within a factor of 2 within the uncertainties for all the sources. And in particular, for our higher redshift sources that cluster around redshift 2.5, all of them agree within the unity line for 5 out of the 6 targets. And so we're really excited by this result because, again, we knew that these calibrations worked at redshift 0. We know they don't work at high redshift necessarily. And now we have very strong evidence that they do work up to at least, say, redshift 2.5. So over the last roughly 10 billion years of cosmic history, we can self-consistently use these to derive metallicities. So now that we have good confidence in our strong line calibrations, we went ahead and applied these to our larger sample in basically 2 flavors. The first are individual targets that have very high signal-to-noise spectroscopy, and the second is by stacking galaxies as a function of mass in order to build up signal-to-noise and push down into additional parameter space. And so these are what those stacks look like, again, for the low redshift on your left and the higher redshift on your right. With the overall stack at the top and then working your way down to lower and lower stellar masses as you move down. The lines look pretty narrow on the left because that's mostly coming from MUSE, and they look relatively broad on the right, mostly coming from the WIFC3 GRISM. But again, just the takeaway there that at the very bottom we're reaching down to less than 10 to the 8 solar masses in both cases. So we go ahead and fit all of our emission lines, apply our strong line diagnostics, and here are our key results. So first we have the mass metallicity relationship for our low redshift sources, looking at the stellar mass versus gas phase abundance of oxygen relative to hydrogen. We have the results for our stacked galaxies in squares. Individual galaxies are circles, and the low redshift SDSS results are the solid black line. Now, we can see that our targets sit quite a bit above this, and we of course know that this relationship is also a function of star formation rate, but in this case, we are actually sitting even higher than the existing calibrations from SDSS. And so what we did was look at how that low mass slope is varying as a function of star formation rate and actually extrapolate it beyond what is covered by SDSS, which is shown by basically those orange and red lines with a shaded region showing the uncertainty in the extrapolation. And so we can see in general, our stacks are sitting pretty well where we would expect, extrapolating to even lower star formation rates, which is telling us that that critical connection between mass metallicity and star formation rate is likely holding at even lower star formation rates than what we probed with SDSS, granted within some uncertainty on that extrapolation. Next, we have our results for the higher redshift sample. Again, with the redshift 0 result for SDSS shown by black and then shifted down by 0.3 dex in gray, with our stacks as squares and our individual galaxies as circles. First thing we see is that they sit about 0.2 to 0.3 dex lower. That's not new, that's well known by a variety of studies. But what is new that we're excited about is this very lowest mass point here. So we pushed roughly 5 times lower in mass and star formation rate than previous studies with the HST at this redshift. and we see that metallicity is continuing to decrease to a value of about 15% solar without signs of a turnover or flattening. So we're seeing that the metallicity is continuing to decrease as we continue to go down into mass. So again, just kind of summarize here, the offset on the left sitting high is due to reaching very low star formation rates, while the offset low on the right, or excuse me, on the high redshift portion is due to redshift evolution. So to go ahead and wrap this up, what we found is that for the strong line oxygen abundance calibrations that we tested, we're seeing that they are valid in comparison with the direct method up to a redshift of at least, say, 2.3, which means that we can self-consistently apply these to derive metallicities over a large portion of cosmic time. Again, we knew that they worked at redshift 0. We're having strong evidence they don't work high redshift, so now we have at least one anchor point in the middle that suggests that they work at intermediate redshifts. We've used that to extend the gas phase mass metallicity relationship at redshifts 1 to 2 down to about 10 to the 7.5 solar masses, and see that the metallicity continues to decrease down to about, say, 15% solar without seeing evidence of that flattening yet in the mass metallicity relation. And finally, I'll just mention that the key reason we chose this field is because we have these two very bright background quasars that we can use to probe gas and absorption. And so for more work on how we're taking these galaxies that we viewed in emission and how we're connecting them to the gas that's seen in absorption, go ahead and please see the poster by Alex Beckett. And with that, I would be happy to take any questions.
Excellent. First question.
Hey, Mitch, nice talk. Super interesting stuff. This might come out more as a comment than a question, so apologies for that. So one of the tricky things with the Curti calibrations is that above a redshift, a metallicity of 8.2 or so, it's based on the stacks. But below that metallicity, it's based on individual 4363 detected SDSS objects. If you plot them on the stellar mass star formation rate plane, they are all much higher specific star formation rate than the redshift 0 main sequence. And so basically at high metallicity, it's fit to normal galaxies. At low metallicity, it's fit to redshift 2 analogs. And there's kind of this like discrepancy between at low metallicity, that calibration is fit to extreme ISM conditions objects, which is mostly what lined up with the ones that you were able to test with the direct method. And at high metallicity, it's fit to normal star forming galaxies. And so I wonder if this lack of evolution in the calibrations you've seen is because in that low metallicity part of the Curti calibration sample, it's actually extreme local galaxies that they used, individual 4363 emitters, rather than things on the main sequence, things that are in like dwarf galaxies on the main sequence from like Danielle's papers, for example.
That's a very interesting point. I think we should take that one offline because that's going to require a little bit more chatting. But that's a very good point. Thank you for pointing that out.
Thank you. Any other questions for Mitchell? Well, people think we have one more minute. I was curious, so you're using Muse and GRISM data, so the spectral resolution is different, very different. Were there any specific challenges in trying to?
Yeah, so we fit all of the spectra simultaneously, and they do indeed differ in spectral resolution by more than a factor of 40. And so in this case, there's a variety of constraints that are put in place. So ideally, you want all the emission lines to give you a self-consistent redshift for one target. And we have diagnostics in there that check for any offsets between the two data sets. We find the intercalibration to be excellent. And we also allow a little bit of wiggle room for lines of very different ionization species, particularly if you want to go ahead and like try to include Lyman alpha in that fit, which has a weird profile, things like that. So we did a bunch of checks in order to see that they were behaving well together, and then placed constraints in order to get kind of a reasonable parameter space on that. So yes, there was definitely some unique challenges on that.
That sounds very informative, so maybe we can chat. Any final questions? If not, let's thank Mitchell and the rest of the speakers for the session again. We're moving on to the flash talks. So people presenting right now, if they can come to the front.
I'm not sure how this
Hi, everyone. My name is Juan Pablo Alfonso. I am a graduate student at Tohoku University in Japan. And my poster talks about my recent work called Katachi, which is a new way of decoding galaxy morphology using interpretable CNNs. So the big idea of the project is we have CNNs that can basically take the galaxy image, just a broadband GRI image, and it can recreate the star formation history from that. And the big takeaway that we have is we can get it within the same accuracy as SAD fitting, which was a big jump for us. And the more interesting part of the project, or the second part, is we actually interpret how the CNN is making its predictions. So what we do is generate these heat maps over the images to tell us what part of the image is the network looking at when it predicts certain parameters that we use to recreate the star formation history. What this lets us do is get actual connections between morphological features in galaxies and their star formation histories. And in this slide, I just want to show some of these maps. And we also can do the maps by image, by color specifically. So what it lets us do is like areas that are red are areas of high focus, area of blue are like of low focus. So what it lets us do is the areas that are highlighted are being used by the network to predict, let's say, the mass or the SFR or the D4000. And yeah, using this, we can basically find a link between the star formation history and certain physical properties of galaxies, how they look. Thank you.
Next one. Okay. So I'm Javier Ballesteros Paredes, working at the UNAM in Mexico. So the idea of my poster is twofold. On the one hand, talking about clusters, how if you have a molecular cloud, molecular clouds are collapsing, those are not supported by turbulence. Basically, the idea is that although people believe that Vidia parameters of the order of 1 means they are in equilibrium, in fact, what we found is that collapsing clouds develop a Vidia parameter of 1 after one free-fall time. So after that, then if you have a collapsing cloud and you look at the proper motion of the stars in the cloud, then you will find that the velocity dispersion of the stars is quite constant if the cloud is collapsing. Instead, in turbulent clouds, you will find that the velocity dispersion increases with the mass of the stars. This is for simulations. In the case of the observations, we found very flat velocity dispersions, which means that these clusters have been formed by collapsing clouds. If you then believe that the clouds are collapsing, you can prove that the efficiency per free-fall time is quite constant if the cloud is undergoing Jeans fragmentation. And you also will find that the efficiency per free-fall time is quite small, around 0.01 in collapsing clouds. So you don't need feedback to have these low efficiencies per free-fall time. And then I will try to convince you that you can explain somehow the different Kennywood-Smith relations just through gravitational collapse in a way similar to the work of Bruce 2018. So thank you.
Hi everyone, I am Valentina Latorre, a PhD candidate at Tufts University, and I'm presenting a poster on galaxy parameter estimations using self-organizing maps for large survey dataset. This poster is based on this paper that has been accepted for publication, and this is the QR code if you'd like to read more details about it. And we know that our understanding of galaxy evolutions depends on our ability to derive galaxy parameters, which is already quite a challenge, as we were discussing in these days. But also we need to do so for large galaxy populations that spans different evolutionary stages and different epochs. And so this has given rise to the sheer amount of data from the large volume data sets. And so estimating galaxy parameters has become also a computational challenge. So we are trying to do our best, and in this work, using a multi-band data set from ultraviolet to middle infrared, we are using self-organizing maps, which is an unsupervised machine learning method. And we use this method to group galaxies based on their observed colors. And this method performs a dimensionality reduction, and it provides great visualizations of the data set, but also allows us to accelerate the parameter estimation process, also by a million times faster than traditional SED fitting methods only. So in this work, our focus is on handling missing data, how missing data affect the estimation of parameters. We try to recover missing data with this method. And also we describe how we can derive probability distribution function of the derived parameters. So please stop by, talk with me if you're interested, and also I can chat more on the ongoing project, which is applying this method to real data from the HSC deep survey. So thank you very much.
So hello everyone, my name is Michael Romano. I'm a postdoc at the National Center for Nuclear Research in Warsaw. So in the next 2 minutes, I would like to present you our new results about the impact of star formation-driven outflows on the evolution of nearby dwarf galaxies. We know that because of their shallow gravitational potential, dwarf galaxies are one of the best targets to investigate the effect of outflow on galaxy evolution. And especially in the local universe, they can represent a great opportunity to analyze outflow in such a great detail. So for this reason, we decided to investigate the impact of galactic outflows on the evolution of dwarf galaxies. In particular, we selected a sample of local low metallicity dwarf galaxies drawn from the Dwarf Galaxy Survey. And we used Herschel archival data to observe the C2 emission line at 158 micron, searching for broad wings in the spectra of these galaxies, which are representative of the outflowing gas. So we obtained that for these galaxies, on average, outflows show outflow rates which are comparable with the star formation rate of the galaxies, implying mass loading factor of order of unity. And this is in contrast with state-of-the-art chemical evolution models, which are currently predicting much larger outflow efficiency in order to reproduce the amount of gas and dust in these galaxies. And we also found that galactic outflows are very important for the evolution of such galaxies, because on average, they can drag up to 40% of the outflowing gas outside of the galaxy, so enriching the circumgalactic and also intergalactic medium. So if you are interested in this topic, please come to me, let's have a chat, and come to see my poster. So thanks.
All right, hi everyone. My name is Logan Jones. I'm a postdoc here at Space Telescope. I'm here, as many of us are, because I'm interested in not only the nature of the two-way relationship between molecular gas and massive stars, but then how that relationship changes with metallicity. In these past couple of days, we've had a lot of love for the low metallicity regime. I'm here to give some love to the high metallicity regime by taking a dive into the 2 to 3 times solar starbursting core of M83. So we have a set of 4 MIRI MRS pointings covering the nucleus of M83. And basically one of the first, like, the amount of just like information in this data set is ridiculous. But so I'm just going to basically share a couple of things that we're seeing now that we're going through looking at it spaxel by spaxel. What we're finding basically is that these different H2 molecular transitions are excited to different degrees as you move across this field of view, with most of the warm H2 emission coming from this very dusty cloud, a little bit from the optical nucleus, and then progressively less as you move kind of clockwise through these regions of older and older stellar populations. The excitation modeling that we've been doing is suggesting that the molecular gas warmer than about 200 Kelvin accounts for roughly 2.5% of the total molecular mass in this region. But given how steep the power law models that we're using are, if we were to extrapolate those to, for example, 100 Kelvin, then we potentially start running into a problem of having more H2 gas than what could be inferred from the CO. And so this question of is there a substantial fraction of CO dark gas even in M83 in a supersolar environment like M83 has very interesting connotations for star formation. If you want to learn more about this and then also this potential age gradient across our field of view, come see me at my e-poster.
Hi. My name is Peter Zeitler. I'm an ESA-Aura astronomer here at STSCI. And I want to quickly introduce you to our preliminary recent results of the young SMC star cluster NGC 602. And compared to the other star clusters Alec presented this morning, this one is actually located in the wing of the SMC, so in a very low density calm region of the ISM. And it can be interpreted as like a low metallicity analog more to Trample 14. So you have a lot of like O and B stars in the center. And we now have data from the far UV with STIS from the most massive stars to like the 25 micron mid-infrared in MIRI. So this is the JWST NIRCam data. And we are studying like how the Freeman sequence stars and the protoplanetary disks and the YSOs evolves in this environment, especially under the winds and radiation of the OB stars. And so far, that thing should not be over there yet, anyhow. This should be the next slide. Anyways, what you should see is like there are actually 3 stream-like features of Freeman sequence stars. They are the red ones identified in the color magnitude diagram. And it looks like there are 3 stream-like features of young stars, similar to what we found like 2 years ago in NGC 346 with Hubble proper motions and Muse radial velocities. And it also looks like that the gas is more, so there is less gas of the H2 region left in those regions. So either used by the star formation itself or cleared through radiation feedback. And my poster hangs over there where Isha is standing. Thanks.
Okay, so I think that's it for this session. Let's go get coffee and check out the posters. Thank you, everyone.